Here is what a 305 second ISO 1600 Master Dark looks like for my Nikon D5300. This is a pretty noisy Master Dark, so you can imagine how noisy an individual dark frame is. Here is the histogram for the Master Dark. The standard deviation A values are much higher and vary quite a bit. The average standard deviation G value is 11. The average mean value is roughly 608, which is very close to the black ADU value for this camera. The black ADU logic in this camera is working hard, but it's not perfect. Here's a 182nd ISO 1600 Master Dark for the Canon 750D. Lots of hot pixels, but no cold pixels. Here's the histogram for the Master Dark. The average standard deviation G value is 23. The black ADU logic is working well here. The average mean values are very close to 2048. Here is a 202nd Master Dark for my QHY 294C. Lots of hot pixels with no hint of cold pixels. Here's the histogram for my QHY 294C. The average standard deviation G value is 17.9. The average mean value has grown from 21 for the Master Bias up to 120 for this Master Dark. It's this increase in the average mean value that is indicated in that dark current graph I showed you earlier. Here is the Master Dark for the ASI 2600MC Pro. Lots of hot pixels and a few cold pixels. Here is the histogram for the Master Dark. The average standard deviation G value is 1.1. The average mean value is 52, which is virtually the same as the 51.7 value for the Master Bias. Clearly, there is virtually no increase in average mean value, which is a big selling point for this camera. Phew! All those masters lead up to this table. Only my Nikon D5300 and QHY 294C Master Darks are different exposure lengths. In order to be able to compare all four cameras, I need to adjust the Master Darks so that they were effectively the same exposure lengths. To accomplish this, I used what amounts to a dark scaling equation to figure out how to adjust the photons per count value. I chose to call these adjustment values scale factors. So now I can show you the Master Darks for the four cameras, but I'm going to rescale the y-axis so that it equals photons. This will allow us to compare these four cameras from the aspect of how much their dark current can affect your light frames. Here is the Master Dark for my Nikon D5300. I've applied the scale factor and relabeled the y-axis as photons. So this graph indicates how many photons will effectively be mimicked by the camera's dark current for a 180-second exposure at ISO 1600. The Iris Nebula photos I showed you were for 200-second exposures, which are pretty close to the 180-second benchmark I'm using here. You will remember the hot pixels that Deep Sky Stacker was able to eliminate. You will also remember that eventually we could clearly see the walking noise, which is solely due to the camera's dark current. The dark current in my Nikon D5300 is adding roughly 10 to 20 photons in a 180-second exposure. These extra photons are essentially noise that remains visible even in Kappa Sigma stacked images. 20 photons over 180 seconds translates into 1 photon every 9 seconds. That's an amazingly low rate of accumulated photons. But we know that this dark current was visible on my Iris Nebula astrophotos. The good news is that the effects of dark current can be calibrated out of our light frames by using a Master Dark. Before I go to the next slide, I want to let you all know that I have modified my Nikon D5300 in such a way that its dark current has been reduced by 50%. It's fair to say that a stock D5300 would have twice the noise as what is shown here. Better still, I am willing to show you exactly how to modify your stock DSLR to accomplish this same 50% reduction. Have I got your attention yet? Here is my modification. I made a bracket that holds a computer fan from an old computer. The fan is powered by 12 volts via the RCA cable shown. The articulated LCD screen is pivoted out of the way so that the fan can blow ambient air directly onto the rear of the camera. The fan helps the camera get rid of excess heat. This causes the imaging chip to run cooler, which significantly lowers its dark current. DSLRs are not designed to run for hours. Excess heat can easily build up in the camera, causing the camera temperature to easily soar into the mid-30 degrees Celsius range. The cooling fan can dissipate upwards of 6 degrees of this excess heat. It's a known fact that the dark current in an imaging chip will double in magnitude for every temperature increase of roughly 6 degrees Celsius. So here is a camera modification that you can do yourself. It will cut the dark current in half. Because it's blowing ambient air out of the camera, there's no risk of causing condensation to occur inside the camera. Okay, let's carry on with our camera comparisons.